So, welcome to the series of our lecture series on fields and differential operators. In the last class we studied about the divergence, and for today's class we will study gradient and curl. We have already studied that when a del operator operates on a vector field, this results in a scalar field, and this scalar field is actually the operation of del on a vector field is actually the flux of the field A through the surface area S bounded by the volume. So the volume is divided per unit volume, so the volume is divided. So this is delta V, where the volume is supposed to be very small. So in mathematical notation we write it limit delta V tends to 0. So this is about divergence, means the operation of del operator operating on a vector field results in a scalar field which is a flux. Now today we will see what this operation results in on a scalar field when this del operator operates on a scalar field. This is called the gradient of the field phi, and this results in a vector field. Okay, so we are discussing this is called gradient, and then we will discuss what this operation del operates when cross product with the vector field A. This is again a vector field, and this field is called the curl of A. So first of all we will start with the gradient. So the gradient is an operation of del on a scalar field. It's called gradient. So the gradient operator operates on a scalar field. Scalar field, and the resultant is a vector field. Is a vector field. Okay, you are operating on a scalar field, but the result is vector field. The gradient of any arbitrary field, any arbitrary scalar field phi is written as or grads phi. You can write like this also, or like this also. Is the means gradient of phi. So it's grad phi. So this grad phi is a vector and the direction of this vector is along the increasing value of phi. So the grad phi at any point gradient phi acts is directed along the increasing value of means this vector grad phi is a vector whose direction is along the increasing value of phi, where the phi increases. In that direction it applies. Okay. So suppose we have a scalar field like electrostatic potential. So the electrostatic potential is a field generated by the charged particle, and this is a scalar field. If you take the gradient of that field, of electrostatic potential field, you will find that it is equal to the electric field, which is a vector field. Right. Suppose this is an example of the gradient. Suppose this is a charged body. This charged body will create a field of potential around it. So this surface will have a potential, say V1, this has V2. Obviously V1 has a more potential than V2. As you increases away from the charge, the potential decreases. So this is at higher potential, this is at lower potential, this is at lower potential. So as you come closer to the charge, the potential increases. So if you take the gradient, means suppose we consider only the x component. So if you take the potential with respect to x is the displacement from this, x is measured from here, from the charge, center of the charge. This is the variation of potential with respect to the x. And this is equal to the electric field, which is a vector quantity. And the minus sign here symbolizes that as dx increases, this value decreases. Potentially, as you go away, the potential decreases. As you come closer, this becomes. So this is the x component. So this gradient of the potential is actually dv by dx I plus dv by dy j plus dv by dz. Okay. And we know that the relationship between, if you consider the only x component, this will be the x component only. So dv by dx is actually the electric field along the x-axis, and this has a negative sign here because as it increases the displacement, as you go away from the charge, the potential decreases. As we come closer, the potential increases. So this is the x component of the electric field. So this is the y component of the electric field, this will be the z component of the electric field. So this is one of the examples how the gradient of a scalar field, particular scalar field, results in a vector field. Now come to the curl. What's the meaning of curl? So the curl. So curl of any arbitrary vector field. Curl of any arbitrary field A, written as is the measure of rotation of the field. This applies only for the field which is rotating fields, where A is a field which is like this. If the field is like this, so the curl of A means integral of A along this whole path divided by the area enclosed by this one. So the curl of A, or you can write it as curl A, is actually a measure of A along the holes. So it is line integral of A divided by the surface which is inside this whole circle. So the circuit surface is d delta s, and assuming that delta s is very small, so limit delta s tends to 0. This is the meaning of curl. Curl is the measurement of the whole line integral of this vector field. We will take the example, one of the example, and see how is it. And this is a vector quantity. The curl of A is a vector. This is a vector field. Curl A is a vector field directed along. And what is the direction of this field? If this is a vector field, its direction is perpendicular to the surface. This surface. The curl of V is a vector directed perpendicularly to the surface. Say delta S. This is one of the example of this curl is the Ampere's law, because we know that in Ampere's law the magnetic field, the rotation of the magnetic field, this is the magnetic field, they take the rotation of the whole magnetic field, line integral of the magnetic field, results in a current which is directed perpendicular along the axis perpendicular to the plane formed by this circuit. You know that when a current passes in this direction in Ampere's law, then the magnetic field will form along this, just like this. If the magnetic field is along the fingers, the thumb will point the direction of the current. So this is the rotation of the line integral of the magnetic field. This is the line integral of the magnetic field is equal to the current. So this is equal to, in Ampere's law we have seen instead of A dot, this is B dot dl. This is the Ampere's law. Magnetic field, line integral of the magnetic field results in a current I. This is Ampere's. So this is one of the examples. Now, we take an example of rotation of, suppose, air or any fluid. Suppose a fluid is or air is rotating is with certain velocity v along a circular path. But the fluid is rotating like this. Okay. So what we do, take the figure. Take the x component, x-axis and y-axis, this is the origin, and the velocity is along this direction. This is the velocity of the fluid, and suppose this is the radius, the velocity at this point, and this is the angle. So this, if suppose the angular velocity is omega, then v can be written as velocity of the fluid on a circle of radius r. So velocity of fluid along a circle of radius r is v is equal to r omega, where omega is the angular speed, where omega is the angular speed. The magnitude of the velocity will be equal to r times omega. Okay. Or if you write take the x component I, y component, v can be written as this. So v is, which is equal to vx I plus vy j. So it is, we are resolving this v into two components along is the x component, this is the y component. The velocity along the x-axis, if this is theta, then this will be also be theta. Because this is theta, 90 minus that is theta. If you resolve this velocity along x and y direction, so this will be vy along the y, velocity along y, and this is the velocity along x-axis. So the velocity along x-axis, this can be written as value of vx is equal to r omega. Okay. Vx will be v sine theta and vy will be v cos theta. If this is really, its component along vy will be v cos theta, and this is along x-axis, so its component will be v sine theta because the angle theta is here. So this will be vx will be v sine theta I, but its direction is opposite to I because it's directed this way. The I is the unit vector along the x-axis, but this is opposite to the x-axis, so it is minus sign here. Plus vy. Vy is equal to v cos theta. V cos theta along the z-axis, on the y-axis, so it's j. Now, but the magnitude of v is given by r omega. So it is r omega, take the v outside the bracket, r omega minus sine theta I plus cos theta j. Now what is sin theta? So if you take this, this is theta, this is r, this is r. You take this is x, this is y, this is x, y. So in that case, we sin theta is equal to p by h, y by r. So y by r times cos theta is b by h, so x by r. So if you take r and r will cancel out, you are left with minus omega I plus omega x j. So we have resolved the velocity into x and y components. Okay. If this is the velocity of the fluid at any point on the circular path, we resolve velocity into x component and y component, and x component will be minus v sin theta I plus y component will be v cos theta j. V is the value of v is given by r omega, taken out. Sin theta can be written as, if this is theta, this is r, this is x, this is y, x and y coordinates. So if you have drawn this figure here, so cos theta means base by hypotenuse, and sin theta is perpendicular by hypotenuse. So it will by x by r cancel out. So this is all about v. Now we want to take the curl of this v. So the curl of this v, our aim is to find the curl of v. The curl of v means curl is del y del x plus del y j plus del y del z. Okay. This is the curl. This is the del of it. And so I am moving these things. It is and v is given by minus this cross product between them, minus omega y I plus omega x. So we know that how to take the cross products. You can take here also I cross I will be 0 and I cross j will be k, or you can take like this dot. You can take I j so del by del x, del by del z, and cross is this minus omega y plus omega x. See? Because we know that we can, just like a cross b is equal to I j k ax ay az bx by. Similarly, you take the I component, these two you will this will multiply with ax ay bz minus b. So same case here. You take the ith component, you have to hide these rows and columns, multiply this minus this, so it is 0, so it will be 0 minus this is differentiation with respect to z, there is no z here, so it will be 0. Now minus j. Minus j, you hide this rows and columns and this rows. So del 0 by del x, 0 minus. This will again be 0. Because this differentiation with respect to z, there is no z here. Now the k component. You hide this column, this rows. So del omega, del x by del x. Omega is constant, angular velocity is constant. Del x by del x will be 1. So omega del x by del x is 1. Minus, but there is minus here. That will be plus. Omega del y by del y will be 1. So it is 2 omega k. It means the rotation of the velocity or the curl of velocity is a vector which is along the z-axis. If you take it, we have taken the rotation along x-axis and y-axis, but the result is a vector which is along the k, along the z-axis, whose magnitude is given by 2 times the angular speed. So this means the curl. Curl is a vector field which is perpendicular to the plane formed by the rotation of the field. So if suppose we have a field like this, and a field like vector field like this. Say this is the vector field A. You want to take the curl. So the curl of A means rotation of the field, but this field is not rotating. This is a parallel field. So this is 0. This type of field gives you 0. Now suppose we have a field like this. Radially outward as gravitational field or electrostatic field. Charge is here. The electric field is radially outward. So this is the field A. If you want to find the curl of this field A, it will again be 0 because there is no rotation of the field. But if the field is like this, any field which is like this, the curl of this field is not 0. If this field is again A, this is not 0 because this curl means the values, the line integral, the whole value of A on this line, and this results in a vector which is perpendicular outward. So this is not 0. So a field like this gives you a vector field, but these types of field gives you the curl of field 0. This is all about divergence, gradient and curl. We will do some problems or some formula related to these divergence, curl. I will write some of the formulas. So if you take formulas related to del operator, formulas or sometimes it is as formulae also. So if this del operator acts along two scalar field, sum of scalar field, this will be equal to gradient of phi plus gradient of psi. This is the gradient of sum of the two. or this is grad phi plus psi is equal to gradient phi plus gradient. I should take this the first, second form. If you take the divergence of the sum of two vector fields, A plus B. So these are two vector fields. So this will results in the divergence of A plus divergence of curl of A plus B. This will again be curl of A plus curl of B. All these can be proved very easily. It's very simple. Now take the curl or the divergence of scalar field and a vector field. Product of this is a vector field. This is a scalar field and a vector field. Results in a vector field. So it will be divergence. This will be just like you can remember it by just the product of two functions. This is the del operator, is the differential operator. First operating on this and then operating on this. Take the curl. You have to take divergence, this is the curl. This is again just divergence. You can remember it just like this is a product of two functions. First operating on this and the curl remains outside. Then the phi curl of A. A cross B is a vector field. The cross product of two vector is a vector. And this is the divergence because this is a vector. So the divergence of A cross B. It will be equal to B divergence of A what's curl of A minus A curl of B curl of A minus A curl of B. It's just like in the vector we have A dot B cross C is equal to B A cross C minus C A cross minus B A cross C. This is some symmetry like this. In vector we have A B cross C. If you take this cross product and you take the dot product, this can be treated as B C A cross B minus B A This is simply like this. So this is just like this. This we know from vector dissolution. See, this is A, B, C. CAB minus BAC. This just to remember how to remember this formula. Just use this. Now the seventh. Curl of A cross B. Because here it was the divergence of A cross B, it's curl of A cross B. So it is B del A minus B divergence of A minus A minus this is the gradient of A dot B. A dot B will result in a scalar field. And if you apply del, this becomes the gradient of A dot B. So A dot B will be equal to B ninth. This is scalar field. This is the gradient of the scalar field. And divergence of the gradient. This is written as del square phi, or in expanded form this is del square by del square phi plus del square by del y square phi plus del square by del z square phi. Or this is called Laplacian operator. This is the Laplacian operator. Now this 1, 2, 3 relations there are. So if you take the curl of a gradient, this is scalar field and the gradient of scalar is vector. So this vector field, and this is the curl of the vector field. So if this is results in a 0. It's called curl of gradient. So the curl of gradient is 0. Similarly, divergence of curl is also 0. Divergence of curl. Curl, this is A cross, del cross A, this is curl of A, means the rotation of A, and take the divergence of this will go 0. But the curl of A, this will not be 0. This will be equal to del minus del square this you can assume that this will be 0 because this is a gradient. Gradient means any field. Gradient means it's directed along tangentially along the increasing direction of value of phi. So if there is a field phi here, and to take the gradient means suppose there is a field here, scalar field everywhere, some points. You take the gradient, suppose along x-axis, it means along the increasing x direction. So this is a field which is along the x-axis. If you take the curl, we have just seen that this type of field, the curl of this type of field will be 0. If this field is along any one direction, it's not rotating. So this will actually obviously will be 0. Now the curl of A, curl of A means A is in a field, and to take the curl, suppose this is a field A, curl of A means the line integral of this, and this that along perpendicular to the plane formed by this surface, and take the divergence. If you take the divergence of this, it will be 0 because divergence is the flux per unit volume. So this will be 0. And this is the final result. So all these formulas are related to del operation, and we can solve. Some of them are easy to prove. I will prove some one which are tougher one, and we'll do some problems in the next class. Okay. Thank you.